Okay, we've got some more to factorise now. Let's have a look at those. Let's do A. We better factorise that using a completing of the square technique. Now we've got z squared plus z. Now completing the square, we get plus a quarter and then minus a quarter, and then we had the 4 there anyway, which gets us z plus a half squared, okay, plus 4 minus a quarter gets us 15 over 4, doesn't it? Yep. Okay, now we can go with the difference of two squares again now, and we can factorise that very effectively, as you can see there, and our linear factors become there. Yeah? Very nice, isn't it? And another thing there, you see, if we set that polynomial equal to 0, we would get z equals minus a half plus or minus this root 15 over 2i, wouldn't we? Yes, we would, and they are complex conjugate pairs, okay? Great. Now, next one, another nice little quadratic, and we're going to factorise that by completing the square as well. We better take the 2 out, and we've got left that little beastie in there, and we're going to complete the square inside the bracket, aren't we? Yep, there it goes. So we've got z squared plus a half z. Now, half of a half, this coefficient is a quarter. A quarter squared is 1/16. So plus a 16th minus a 16th, and we had that 3 over 2 there anyway, and we're going to harvest this bit of it as a perfect square. It's going to be z minus a quarter all squared, and then we're just going to combine these two terms for the rest of it. Yeah? That's what you get, okay? And now we're just going to turn this into a difference of two squares, and away we go. Yeah? So that's what you get after you turn that into a difference of two squares, and then we can just combine those now into linear factors like that. And if we were to make this thing equal to 0, if we did that, we would find that z would be a quarter plus or minus root 23 over 4 times I, and they would be complex conjugate roots, wouldn't they? And as you can see again, with our fundamental theorem of algebra, we had a quadratic and we've got two linear factors. Yeah? Great. So let's move on now, having triumphed over A and B, and we'll have a look at Mr. C. Now, he's a pretty prickly looking customer, isn't he? Look at him. And unfortunately, you can see that this coefficient here, of this 4z into 5 minus I term, the minus 4 into 5 minus I is not a real coefficient, and neither is this 48 minus 20i. That's not a real coefficient either, or it's not a real number. So therefore, the conjugate root theorem does not apply, okay? But we do know that it'll factorise into two linear factors. Okay, let's just see what we get by trudging through the algebra with this thing. We're going to complete the square, so let's go. Now, just fasten your seatbelts. It's not that ghastly. It won't be fun, but it's not that ghastly, okay? Just take out the 2 for a start, and we get that there. Have a look, have a look. Yeah, you're right. Now we're going to complete the square by halving this term here, and then squaring it, okay? There it is, okay? So half of 2 into 5 minus I is just 5 minus I. Then you square that term, then take it away again so that you haven't changed the overall value of what you've got here. And we already had that term there, the 24 minus 10I. Okay, now let's do the next line. So we've got here this and this and this as the same as what we had before. Now I've just expanded out this minus 5 minus I all squared term, and in the next line I'm going to remove that bracket and then combine all this stuff here on the end to see what's left. Okay, alright, so yeah, minus 25 plus 10I. Now that's minus I squared, which is plus 1. Plus 24 minus 10I. Oh, look at this. Well, wouldn't you know, minus 25 and then plus 25 and plus 10I and minus 10I. Well, isn't that lovely? So that's all going to cancel out and go away for us. How very fortunate. So what are we left with? We're left with that. Good grief. And this is two linear factors in Z. as I told you, yes? Because it was a polynomial of degree 2. And the other thing is that, do you notice here that the complex conjugate root theorem would not apply? Because if we set that thing equal to 0, we would just have z equals 5 minus I, wouldn't we? And that is only the one repeated linear factor, so it's not real and it's not complex conjugate pairs, you see? So the conjugate root theorem would not apply. Alright, very exciting. Now in this example 3, I'm solving each of the following equations for z, where I've set the 3 previous screen polynomials equal to 0. So okay, we're just going to test out the conjugate root theorem now and just hammer that home for you, okay? Okay, so in the first example A, we determined in the previous screen that would equal this in the factorised form, okay? So therefore, if we're solving the thing equal to 0, we would have that equal 0, yes? And we can see that therefore by the null factor law, we get that, and therefore we get that, okay? And blow me down, these of course are complex conjugate pairs, aren't they? Yes, because the coefficients were real. Yes, great. Now in part B, similarly, from the previous screen, we determined that this polynomial here equaled this in its factorised form. Therefore, if we set the whole thing equal to 0, then by using the null factor law, we get z equals a quarter plus or minus root 23 over 4 times I. Okay, and yes, you know what I'm going to say. These are complex conjugate pairs because the coefficients of this polynomial are all real. 2, minus 1, and plus 3. Yeah? Alright, now this little beastie is entirely different. He does not have real coefficients because this beastie doesn't have a real coefficient, and that's not a real number there. So we don't expect the conjugate root theorem to apply, do we? We found that when we factorise that thing, we got this, yes, and then if we set that equal to 0, of course we're going to find that. And as I said to you on the previous screen, this is just the one repeated linear factor, no complex conjugate pairs, and it's not real. Okay? Isn't that great? Alright, using CAS now, I better show you how to use the CAS. If we go menu on the TI Inspire, we go menu, algebra, complex, which is number C. Okay, menu item C under algebra, that we can either go solve or factor. Okay, solve or factor. But these are complex solve and complex factor. They're quite different from normal solve and normal factor. They enable you to get your complex roots or your complex factors, ladies and gentlemen. If you want to, you can just go to the menu. You can write C and then just go menu 3, 2 for factor or 1 for solve, having written a C in front, and the command will work just the same. Okay? You get that? And let's just go over the screen now and show you how it works. C solve of this prickly little customer, which was part C of the previous example. We just get that. Quick as lightning. Amazing, isn't it? These calculators are mighty, mighty smart.